Hey guys, Mr. Brown here, and I am going to show you how to perform the molar mass of a volatile liquid experiment. To do this lab, you're going to need to gather a few of your materials. You're going to need a heat source and something to hold some water. You will probably use a saucepan or something from your stove, from your kitchen. I would suggest that you use the smallest saucepan that you have that will allow you to hopefully tip the flask over in the pan without having to hold it down in the water. However, any saucepan that will hold water plus the flask here will work. You'll obviously need the flask. We will also need our balance, some aluminum foil, a rubber band, a small pin, a push pin, a safety pin, a straight pin, all will be fine. You will need the 5 milliliter graduated cylinder from your kit. You will need the volatile organic chemical unknown from your kit. And you will need something like a pot holder, a pair of gloves, or maybe even a pair of tongs to handle the hot flask. Once you have everything together, notice the first thing I've done is put on my lab coat. You might want to wear just something that you don't mind getting a little dirty and is well fitting also. And you'll also want to make sure to have your eye protection on. Before I've started anything, I've made sure I've got my eye protection on, and you should as well. Once you have all that set up and ready to go, you can begin your experiment. To do the molar mass of a volatile liquid experiment, the first thing you're going to do is look at your bottle, look at your unknown number there on the label, and write that down or put that down in your data table. There's a spot at the top of the data table up here that says unknown number, and I'm going to write my unknown number in 541. .541 is my number, and I leave it there and move on to the straight mark there. Move on to doing the experiment. It says in step number 2 to cut 2 7 by 7 centimeter squares of aluminum foil. So the 7 by 7 centimeter square should look somewhat comparable in size to this. You will need 2 of them. I'm only going to be showing you how to do the experiment one time, so I only have one, but you'll do it twice and average your results. So you'll need 2 pieces of the foil. Once you have that, the next step is to weigh your empty 125 milliliter Erlenmeyer flask. So you'll need to turn on your balance, let it set and show zeros, and place your balance on the scale. My flask reads 60.82 grams, and so when I write that down, I'm going to make sure that I include all of those significant figures. So in the first box there where it says mass of the empty flask, I will write 60.82 grams. Make that a little bit smaller. There we go. 60.82 grams. I can then take that off of the balance and proceed to step 4. Step 4 says to measure approximately 5 milliliters of the unknown liquid with the 10 milliliter graduated cylinder and pour that amount into the flask. So you're going to take the small graduated cylinder in your kit, you're going to open your volatile organic liquid, and when it says approximately 5 milliliters, that means you don't have to get exactly 5, you can get somewhere close to it. And transfer that into the Erlenmeyer flask. Carefully put that 5-ish milliliters into the Erlenmeyer flask. Then it says to take your aluminum foil and place your aluminum foil over the neck of the flask. Try to get it taut so that you have a flat surface across the top there. Try not to tear it in the process, and secure it with the rubber band. All right, nice and secure. The next part is very important. Don't forget this part, or you may blow the aluminum foil and the rubber bands off of the flask with the pressure that you create. We want to put a very tiny hole right in the center of that aluminum foil over the top of our flask with a pin of some sort. You can use a push pin, a safety pin, a straight pin, any of those should do the trick. One tiny little hole in the middle of the aluminum foil that we have there. Then you're going to take your flask and place it in the middle of your saucepan. Notice that your flask has a scale of measure down the side. We're not using to measure 100 milliliters of water or anything like that, but we want our water level to at least cover up to about the 100 on the side of the flask. So when I put that down in there, I will take my flask and put some water in my heat source. And I will check to see, and the water does come up. In fact, my water comes up just past 100. Right there. The flask should be into the water at about the 100 milliliter mark. Then you will turn on your heat source and let the water come to a boil. Once you have a nice boil going on in the water, you are going to want to take an oven mitt, a pair of tongs. In my case, I've got a nice glove, and use that to set the flask with the organic chemical down into the water. Now, for those of you using a saucepan, you may have to use something to stand it up tall. Keep it standing up. You can use a glove to hold it upright. You can use a pair of tongs to hold it upright. Or you can simply allow it to lay against the edge of the pan if it doesn't tip all the way over. We do not want to let any water into the flask, and we don't want to let any of the organic chemicals spill out. The goal is to have the organic chemical completely evaporate, and so that the gas fills the flask, after which we can condense it and then measure the mass of the condensate. And that will allow us to determine the molar mass of the vapor via the ideal gas equation, or a rearrangement of the ideal gas equation. Because we should be able to determine the volume of the organic chemical gas that we produce. We'll know the temperature by measuring the boiling water temperature. Something I forgot in the materials list, by the way, is the fact that you will want a thermometer in order to measure the temperature of the boiling water. So typically it probably takes between 5 to 10 minutes before all of the organic liquid to evaporate. You can leave it in for 10 minutes if you have a hard time seeing whether or not all of the chemical has evaporated, but we do want all of it to go into the gaseous state before we remove it from the boiling water. So take the temperature of the boiling water while your liquid is evaporating. It should be relatively close to 100 degrees Celsius, especially if you read through the lab pretty closely. You'll see that atmospheric pressure here in North Carolina is typically not much different from 1 atmosphere, and at 1 atmosphere of pressure, water boils at 100 degrees Celsius. So we expect that 100 degrees Celsius is our boiling temperature. Maybe if you're working on this in the mountains, you may see a slight reduction in that temperature. That is the one place that we do see water boil a little bit less than 100 degrees here in North Carolina, because the higher up you go, the less atmospheric pressure you have. Water is able to boil a little bit easier. So allow the flask to sit there between 5 and 10 minutes. Get the water temperature and allow all of that organic chemical to go into the vapor phase before you remove it from the flask. So after about 5 or 10 minutes, we are going to remove our flask from the boiling water. I am using a pair of tongs to do this. You may want to use something as well. And we're going to set it somewhere down safely to cool. So we allow the flask to cool a while, 3 to 4 minutes, until we are able to touch it with our bare hands. While the flask cools, the organic chemical that we have forced into the vapor phase to fill the entire flask will recondense back into the liquid phase. That way, when we take the aluminum foil off, in order to measure how much mass our organic chemical has added to our flask, we don't lose any as it evaporates away. After allowing the flask to cool for some time, you can pick it up with your hands. And to further cool the flask, we're going to take it to a sink and run it under some cold water, but only the sides of the flask. Try not to get it near the top where it would pour water into the flask. That would add unnecessary weight. So rinse the sides of the flask under running water for about a minute or so in order to get the flask cool. Then you'll want to take a paper towel or a rag or something and wipe off any excess moisture and remove the aluminum foil and the rubber band. Make sure there is no moisture on the outside of the flask, only your condensed organic chemical on the inside. There should only be a very small amount in there now. Once you have the flask cooled and wiped off, no external moisture on the flask, you can turn your balance back on and determine the new weight. We should have a little bit more in there than we did before. My balance now reads 61.04 grams. So the mass of the condensed vapor is the difference between these two figures. So I would do 61.04 minus 60.82. That is going to give me a difference of about 0.22 grams. I measured my boiling water temperature while it was boiling to be 102 degrees Celsius. To convert that to Kelvin, we add 273.15 to that figure. So the Kelvin temperature should be 375.15 Kelvin. If you read through the procedure, you'll see that here in North Carolina, our atmospheric pressure, or barometric pressure, doesn't really deviate from 1 all that much. Again, unless you're doing this in the mountains, you may have a little bit lower pressure up there. But that should be accounted for by the difference in boiling temperature. So we can just use, no matter where you are, you can use 1 atmosphere as the pressure figure for your data. All right. The next piece is determining the volume of this flask. We know a lot of things about our vapor. We know its temperature, we know its mass, we know the pressure that it was under. However, we don't know what volume it occupied. Now, these flasks are marked as 125 milliliters. That doesn't mean that they contain exactly 125 milliliters. That means the last markup there is approximately 125 milliliters. However, the vapor occupied the entirety of the flask, including the stuff above that marking there. So we need to know the exact volume of this Erlenmeyer flask. And the way we're going to do that is with the 50 milliliter graduated cylinder that is in your kit. what you will want to do is fill the flat flask completely with water, almost to the exact top. So I have this flask completely filled with water, and we're going to pour into our 50 milliliter graduated cylinder some of that water. We're going to carefully get to exactly 50 milliliters, making sure to measure our graduated cylinder to the bottom of the meniscus, and we can pour that 50 milliliters out down the drain. So that was one 50 milliliter portion from our flask. We'll do another. Exactly 50 milliliters. Being very careful to measure exactly 50 milliliters and pour that out as well. So we have had 100 milliliters total so far. We are finally going to pour this last bit of water in here. I got another 50 milliliters out of mine, so I will dump that out one more time. And there is a tiny bit left. So now I have had 150 milliliters that I poured out, and I have just a very, very tiny amount left that I will pour into my graduated cylinder. And that is not even quite a milliliter of water, so that's about half of a milliliter of water if I'm reading very closely on my lines. So I will say that the volume of my flask, remember, I did 50 milliliters 3 times, and then I have about half of a milliliter left over. So the volume of my flask is about 150.5 milliliters. To convert milliliters to liters, we divide by 1,000. We can move our decimal place to the left 3 times, so that would be 0.1505 liters. Now we have all of the information that we need in order to calculate the molar mass of our unknown. Now we can see with all of our data collected and the procedure performed, we are ready to calculate the molar mass of our unknown substance. So we are going to use the formula we find down here that says the molar mass is equal to mass times the ideal gas constant R times the temperature times the pressure times the volume. We are going to use the version of R that is equal to 0.08205, and the units with that version of R are liter atmospheres per mole Kelvin. And that is the reason we've converted our milliliters to liters as well as our Celsius temperature to Kelvin temperature in order to fit the units on our ideal gas constant. So when we set up the formula, we will do molar mass is equal to the mass, and in my case I had 0.22 grams of organic liquid vapor, 0.22 times the gas constant R, which we've already said is 0.08205 liter atmospheres per mole Kelvin, and the temperature in Kelvin is 375.15 K. We divide all of that by the pressure, which is luckily for us 1, times the volume of the vapor in liters, and my vapor was 0.1505 liters in volume because that was the volume of my flask. When I punch this in my calculator, in order to make sure order of operations is followed, I'm going to put some extra parentheses there and there. And when I punch all of that into my calculator, the result I arrive at is 44.995. So mine actually rounds really nicely to about 45.00 grams per mole.
Now, of course, I can write that here, 45.00 grams per mole. And although it wasn't shown in the video, you guys will also perform the trial a second time, just in order to kind of tighten the data down some, make sure we performed everything correctly and we're getting good results. So in the interest of calculation, I'm just going to assume that I ran the trial a second time, and this time I arrived at a figure of 45.92 grams per mole. Seems reasonable. To find the average of those two, I would add them together, 45 plus 45.92, and then divide by the fact that there are two of them. The average would be 45.46 grams per mole. And if I take a look at the unknown table found in the procedure, my solution is one of these four unknowns, and the only one that I'm really close to is ethanol. So I'm assuming that my unknown substance is ethanol, which has an accepted molar mass, or a really accurately measured molar mass, of 46.07 grams per mole. So my figure is pretty close, but I do have a vested interest in figuring out what that actual percentage of error is there. So to find out the percent error in a data point, we take the absolute value of the difference between the two data points. So the absolute value of my data point, 45.46 grams per mole, minus the actual accepted data point, 46.07 grams per mole, divided by that actual accepted value, 46.07 grams per mole. And we're going to multiply all of that by 100% when we are done. So when it says, remember, absolute value means no matter what the answer comes out to be, whether it's positive or negative, you make it positive. So when I subtract 45.46 minus 46.07, the result is negative 0.61, but because it's an absolute value, I'm just going to put 0.61, because absolute value just turns a negative value positive, divided by 46.07, that accepted literature value for the molar mass of ethanol. And again, multiply everything by 100%. And my error in that case is about 1.32%. Pretty low error, if I do say so myself. So that is the completion of the molar mass of a volatile liquid lab. You will have a few questions to answer on your own. I will leave you to that. If you have any feedback or any more questions, please feel free to email me at brownb@sandhills.edu.